Yeah, so hi everyone, this is Samdam Chaudhary. I'll be speaking about automating awkward array testing. So first of all, let's have a look at the different layers in awkward array. So right at the top, we have the different Python bindings of the C++ classes. That's the layer with which we interact. So after that, we have the C++ classes used for data navigation. And below that, we have the CPU and the CUDA kernels. Now, these contain various kernel functions. So when you try to enter any sorts of array and do functionality on them, so that's the place where all the array manipulation take place. So after this, the rest of the talk is going to be based on the testing on these kernel functions. So this is the current testing infrastructure that's there in awkward array. So we have a kernel specification file that contains various arguments like the kernel function name, their arguments and all. And we have a script called generate test.py that's present inside the dev folder. So when we run this file, so it's going to take in inputs from this kernel specification and it's going to generate a Python kernel here. Now this Python kernel is not a standalone kernel as you saw in the earlier slide. It's just a temporary specification that is generated in order to automate the testing in here. So this is a snapshot of the kernel specification. We've got a kernel function, bit mask array to byte mask array, and we've got all the different arguments, the argument name, the type, the role, and dot. Below that, we have the function definition. This is one of the auto-generated Python tests. So we have all the inputs in here. Now these inputs are hard-coded in the kernel specification file. So the script takes in these inputs and passes it through the Python kernel and gets back the output. And then we have the expected output in here, as you can see in line number 13. And then in line number 15, we again pass these inputs into the kernel, and then we assert whether the result given by the kernel is same as the one we are expecting here. So the one we are expecting here is the one given in line number 13. So the question is, does it cover all the test cases? The answer is no. So what are some of the loopholes in here? There are not too many specific test cases. The testing is not error specific, and the roles of the arguments are not well defined. So what can be a good solution to fill up the gap? We can use something called property-based testing. So what is property-based testing? Property-based testing is a type of testing in which we define the properties of the input and the output that we are expecting. So what are some of the advantages of property-based testing? We can have more hard-coded input data. We can test a larger section of the code base with a very little amount of code, and it's highly efficient and flexible. Hypothesis is one of the greatest examples out there that facilitate property-based testing, and it has tons of features like various strategies to get constraint-based data. We can have highly elaborative test results, regenerate failing test inputs, shrinking, and much more. So here are the different workflows of how a unit test is different from a property-based test. And as you can see, in the first step, we are hard coding the input data in the unit test whereas in property-based test, we are defining the properties and we are letting the computer decide which inputs to generate based on those properties. So here is a sample unit test. We have a sum of numbers that takes in two arguments and it returns the sum of the two arguments. So below we are passing in 2 and 3, and we are asserting whether the result given by the function is the one that we are expecting. So here the output that we are expecting is 2 plus 3 equals to 5. So similar unit test can be written in property-based in this way. So we have many strategies, as you can see in line number 9, where we have defined that the argument 1 and argument 2 are both going to be integers. And it has some properties like minimum value and maximum value. So based on these properties, the code is going to generate various inputs and is going to pass in these inputs to the function sum of numbers. So the plan is that we are going to have a CPU kernel function and pass in these generated input values, and then we're going to assert that the result given by the CPU kernel is same as the one that we are getting from the Python kernel. So in that way, we are going to know that the Python kernel and the CPU kernel are both working fine. So if one gives an error for one input, then the other has to give the same error for the same input.
Santam, 2-minute warning.
So when we run this, we get a highly organized statistical data, and we get like a lot of things like the runtime, the number of failing examples, the passing examples, and so on. So here is one of the approaches out of the many approaches out there that we can implement hypothesis to generate the other corner cases out there that is not there in the unit test. So we have a constraint.json file that stores in all the argument strategies, and we have a script called generate strategy test.py. So it takes in these strategies as an input and then passes it to the Python kernel, and then we hard code the input and the output. So after that, we're going to run the C test and the Python test, and in that way we can indirectly check whether the C kernel and the Python kernel are both giving the same result. So this is an overview of the top. So unit tests may have some corner cases untested, which can be found out using property-based test. And awkward array creates a Python kernel, which is a specification used to auto-generate tests, and the hypothesis library can be used to get a well-documented result of the test cases. I've listed some resources. You can go through them to know more about this. So I would like to thank Jim and Yana for helping me out and being a great mentor to me in this. So thanks a lot. If you want to know more about this project, you can contact me on this email, or if you want to know more about the work that I've done, that's my gift. Thanks.